Have you ever wondered what lies beyond our solar system? What if we could explore interstellar space, reaching unimaginable depths? Introducing Heliospace Travel, a groundbreaking idea that pushes the boundaries of human exploration. Imagine a future where we journey beyond the stars, breaking free from the limitations of our solar system. This bold concept involves utilizing advanced propulsion systems and innovative technologies that propel spacecraft beyond what was once thought possible. It could potentially revolutionize the future of space travel. Heliospace travel revolves around the idea of harnessing the immense energy of our sun and using it to propel spacecraft to incredible speeds. By utilizing the power of the sun and its gravitational forces, we can achieve velocities that were once only seen in science fiction. Imagine the possibilities, exploring distant galaxies, visiting exoplanets, and unraveling the mysteries of the universe. With Heliospace travel, the entire cosmos becomes our playground. Although heliospace travel is an exciting prospect, there are a number of obstacles to overcome, including a requirement for long-term life support systems, the shielding of the spacecraft from cosmic radiation, and the capability of visiting exoplanetary habitats. While still speculative, the pursuit of heliospace travel inspires scientific research, technological innovation, and the exploration of fundamental questions about our place in the universe. Scientists and engineers are exploring novel propulsion technologies, such as solar sails, ion propulsion, and nuclear propulsion, to enable faster and more efficient interstellar travel. Initiatives are underway to design and launch robotic probes capable of reaching neighboring star systems, gathering data, and transmitting it back to Earth. Breakthrough Starshot, for example, aims to develop small, laser-propelled spacecraft for interstellar missions. Breakthrough Starshot is a research and engineering project to develop a proof-of-concept fleet of light-sail interstellar probes named Starship, capable of making the journey to the Alpha Centauri star system 4.34 light-years away. In 2016, Mark Zuckerberg, Yuri Milner, and Stephen Hawking launched the Breakthrough Starshot program. In addition to Breakthrough Starshot, initiatives are underway to discover exoplanets for potential habitability, along with a study of destinations for future interstellar missions. Interstellar travel presents a wide array of profound challenges, such as the immense distances between star systems that require spacecraft capable of sustained travel over thousands of years, posing challenges related to propulsion, power generation, and human longevity. As spacecraft approach the speed of light, relativistic effects such as time dilation, mass increase, and energy requirements become major obstacles. Interstellar space exposes spacecraft and crew to high-energy cosmic rays and other forms of radiation, necessitating effective shielding and radiation protection measures. Maintaining sustainable life support systems for extended durations, including food, water, air, and waste recycling, presents a considerable challenge. Accurate and reliable navigation over vast distances, without the guidance of familiar celestial landmarks, requires advanced autonomous systems and interstellar mapping technology. With vast interstellar distances, communication delays pose a significant challenge, impacting real-time decision-making and the ability to remotely control interstellar missions. Potential encounters with interstellar dust, asteroid-like objects, and other natural hazards along the journey require robust spacecraft shielding and hazard avoidance strategies. The psychological impact of prolonged isolation, confinement, and exposure to the vastness of interstellar space on crew members presents a significant challenge. The energy demands for sustained propulsion over interstellar distances, as well as power generation, place substantial constraints on spacecraft design and technology. The immense cost and long-term commitment of interstellar missions raise economic and political challenges for international collaboration and sustained support. Research into closed-loop life support systems, space habitats, and long-duration human spaceflight contributes to the development of technology necessary for sustaining life during extended interstellar journeys. Advances in spacecraft design, materials science, and autonomous systems are driving innovation in the creation of robust, reliable spacecraft capable of withstanding the rigors of interstellar travel. Understanding the cosmic radiation environment, interstellar medium, and potential hazards of interstellar space is essential for developing shielding, navigation systems, and mission planning for heliospace travel. Protecting spacecraft from cosmic radiation during interstellar travel involves several potential strategies, such as the use of dense and effective shielding materials, such as lead, tungsten, or composites, to create physical barriers that absorb or deflect incoming cosmic radiation. The employment of strong magnetic fields generated by superconducting magnets will work to deflect charged particles away from the spacecraft, reducing radiation exposure. The basic principles of magnetic shielding can be explained as follows. Superconducting magnets or electromagnetic coils aboard the spacecraft generate strong magnetic fields. These magnets can be arranged in specific configurations to create a protective magnetic shield around the spacecraft. When charged particles, such as cosmic rays, encounter the magnetic field, they experience a force known as the Lorentz force. This force causes the charged particles to change their direction of travel, deflecting them away from the spacecraft. The strength and configuration of the magnetic field are crucial in determining its effectiveness as a shield. By adjusting the strength and direction of the magnetic field, it is possible to control the trajectory of charged particles, guiding them away from critical areas of the spacecraft. Designing an effective magnetic shielding system involves optimizing the strength and distribution of the magnetic field to provide adequate protection. Furthermore, power considerations play a significant role, as generating and maintaining strong magnetic fields requires a stable power supply. Magnetic shielding can be integrated with other forms of radiation shielding, such as physical barriers and biological shielding, to provide comprehensive protection against cosmic radiation. Magnetic shielding, while effective at deflecting charged particles, has certain limitations when it comes to providing comprehensive radiation protection. These limitations stem from the nature of magnetic fields and the types of radiation encountered in space. Since neutrons are electrically neutral, they can pass through spacecraft structures without being greatly impacted by magnetic fields. Magnetic fields have a trivial effect on deflecting gamma rays, which are high-energy electromagnetic radiation. High-energy particles can penetrate magnetic fields more effectively, posing challenges for complete radiation protection. Generating and maintaining strong magnetic fields for shielding requires significant power resources. Designing and integrating magnetic shielding into spacecraft adds complexity and mass to the overall spacecraft architecture. Balancing the benefits of magnetic shielding with the added mass and system complexity is an important consideration for mission planners. Magnetic shielding needs to be integrated with other radiation protection methods, such as physical materials for absorption and reflection, to create a comprehensive shielding strategy. Incorporating water or other hydrogen-rich materials into the spacecraft's structure, as hydrogen atoms are effective at slowing down and absorbing radiation. Utilizing a surrounding layer of gas or plasma around the spacecraft to absorb and mitigate incoming radiation, providing an additional layer of protection. Designing spacecraft with areas of increased biological shielding, such as dedicated storm shelters or bunkers, to provide crew members with additional protection during radiation events. The strength of the magnetic field required for shielding influences the power requirements. Stronger magnetic fields require more energy to generate and maintain. The size of the spacecraft area to be shielded and the shape of the shielded region affect the power requirements. The duration of the mission and the need for continuous magnetic shielding influence the power requirements. Long-duration missions require a reliable and sustainable power source to maintain the magnetic field throughout the entire journey. Redundancy and safety considerations may necessitate additional power reserves for backup systems and emergency scenarios, adding to the overall power requirements. And these are just a few of the myriad challenges in designing such a propulsion system. While still speculative, the pursuit of heliospace travel inspires scientific research, technological innovation, and the exploration of fundamental questions about our place in the universe. Thank you for joining Time Pilgrimage on this adventure. And as always, don't forget to like, comment, and subscribe to our channel for more captivating time and space-related content.